online just yet, but I do want today in class, while we're going through this, I'm going to be calling on some folks. So if I call on you, and well, if I can't see you, I probably am not going to call on you, and you're missing out. So I'll turn your cameras on, make sure you can unmute as needed whenever I do call on you. All right, let's dismiss that. There we go. Now, yesterday we talked about, you'll remember we started discussing radicals. And when we looked yesterday at our basic, kind of square roots, cube roots, and things of that nature, we were looking at numbers, okay? We were dealing with the radicand was often like a perfect square, like 144 or 289, a perfect cube like 64 or 27. And so yesterday when we worked with these, it kind of worked out nice and neat. Today we're going to start off with some examples that are perhaps just the opposite of that. They're not numbers, they are variables, okay? So what you're going to do is you're going to learn in today's lesson how to simplify out some radicals that aren't just a nice, neat, what's the square root of 25? Because those are some basics, okay? I will remind you also, while it's on my mind, that you've got a Delta Math assignment from yesterday's lesson that's due today, and you've got one from today's lesson that is due tomorrow. I'm having my ninth graders kind of work similarly to what you guys are doing. So log on to Delta Math if you haven't already, and take care of those two assignments from 8.1. Hey, let's look at this first example right here. And what I'd like to do is just throw this open to the whole class. We're looking at the square root of x squared. And I want to know, what do you think? What do you suppose that might equal, considering that we dealt with inverse operations yesterday? We said like squaring and square rooting sort of undo each other in this way. Somebody unmute and say, what do you think this is going to end up equaling?
X.
All right, good. Pretty popular answer there. So what we're going to do is, as an exercise, I'm going to treat this like a hypothesis in your science class, okay? So like, Tiago, do we just, when we've got a hypothesis like this in science class, do we just assume that it's correct?
No.
Yeah, what do you try to do in science when you've got like such and such hypothesis?
Prove it.
Yeah, you kind of test it out. You put it to the proof and you see, okay, well, is this actually accurate? So what I'm going to do is, as an exercise, in this exercise, I'm going to ask you guys to take diligently down some notes. We're going to split this up into three sort of categories here. Let me get Paul on in here. We're going to split this up into three categories. The first one I'm going to pick here in red. I'm going to say, why don't we just let x, suppose that x is some positive number. Like I'll make x equals 3. Okay? So we'll just make x equals 3. And we'll say, okay, what happens is, I think Jake had said x. Jake's hypothesis here, let's see if it checks out for a positive number like 3. Okay, so on the left side, we're going to plug in 3 for x. And we're going to see, does that equal the right side, plugging in 3 for x. Okay, so 3 squared is 9, obviously. And the square root of 9, we said yesterday, equals 3. And so we don't really have any work to do on the right-hand side. So 3 on the left, 3 on the right. Does that work? Of course it does. Okay, so hypothesis looks pretty good so far. Next, we're going to look at, suppose that x equals 0. Okay, so we talked about a positive number. Let's talk about a neutral number. So x equals 0. Does this work? Okay, so we got square root of 0 squared. And we want to see, does this equal 0? All right, so the left-hand side, 0 squared, again, is pretty easy. 0 squared is 0. Does anybody know what's the square root of 0 on the left-hand side? Well, if you didn't know, square root of 0 is just 0, okay? Which means, hey, that works out pretty well. We got 0 on the left, 0 on the right. Checks out there. Paul, I'm seeing you got ashes. I had forgotten today's Ash Wednesday, so happy Ash Wednesday to you guys that are Catholic. And then, yeah, okay, so look, now we've checked a positive x. We've got a neutral x. Let's look and see if this supposition, it works out for a negative x. So maybe like, let's say x equals -5. We'll do -5 here in orange. Okay, so on the left, I'm going to plug in -5 for x. And we want to see, does that equal plugging in -5 on the right? Okay, so the left-hand side, we work it out, -5 squared is 25. And we said yesterday square root of 25 is 5. And yet over here on the right, we've got -5. And so we say, womp, womp, doesn't work out there. So this hypothesis is nice for 2 out of the 3 scenarios. Okay, so I'm going to ask you a tough question right here. I'm going to say, somebody pipe up. Tell me, what could we do to our little blue hypothesis here to make it such that it works in all three cases? It works in red, it works in green, and it works in orange here. What do you guys think we might do? What are some ideas? Tiago, I see a hand up. What's an idea?
You can say that it's equal to x if it's not a negative number.
Okay, so kind of trimming the fat, so to speak, saying, well, if the orange part gives me trouble, let's just throw the orange part out. And while we could do that, it's just a little, it kind of leaves a bad taste in my mouth, because I would like for this nice hypothesis to work for any x value. I really would like for it to work for any x value. So Tiago, that might work. Drew, I see you've got a hand up. What do you think?
Add a positive or negative sign.
Okay, good. So somebody suggested that in one of the earlier classes. I kind of like that, right? Positive or negative. But in that case, it's kind of like you got to do one or the other. You can't do both, okay? So like, in other words, if x is positive, it works. And if x is negative, it works. But again, kind of just leaves a bad taste in my mouth, so to speak. It's not going to be a positive or a negative. I'll take one more guess. Lewis, I think you had a hand up. What's your guess?
The absolute value.
Holy moly. I think that looks great. Okay, so check this out. Watch what happens now, fellas. Okay, Lewis is correct. What we've got now is we've got a hypothesis that's going to work in all three cases. So on the left side, I'm not really changing anything, but watch how this changes on the right side. Absolute value here in red, absolute value of 3 still remains 3. In green, absolute value of 0 still remains 0. But look at what happens in orange. The absolute value of -5, it becomes +5. And then that means, oh man, the left side does equal the right side. Winner, winner, chicken dinner. Okay, so just as an exercise, what we've done is we've sort of gone through and we've shown the following definition. I'm going to put some stars around it. I'm going to say, hey, man, memorize this little fact as soon as humanly possible, that the square root of x squared equals the absolute value of x. And the reason that that's the case, I'm going to type something up here you guys can write down as well, is that roots, or we'll say even roots, as opposed to an odd root. Okay, so even roots are non-negative by definition. In other words, what that means is that when mathematicians set up this whole notion of square roots, you might have actually noticed that I kind of skimmed over that part right down here, right? Where I was saying, oh, we know the square root of 25 is 5. Well, do we really know that? Like in your elementary school, your teachers have taught you, hey, the square root of 25 is 5. And that's like kind of a math fact that you memorize. Well, why is it that? Why is the square root of 25 5? You ever thought of that?
Because 5 times 5 is 25.
Ha ha! Who said that?
Lewis.
All right, so I'm only seeing from the nose up. That's why I couldn't see your mouth moving. So like Lewis just said, because 5 times 5 is 25. I was hoping that somebody would say that. Well, guess what, Lewis? -5 times -5 is also 25. So how come the square root of 25 isn't -5? Boom, mic drop, okay? Well, you say, well, Coach Morgan, we just didn't learn it that way. What that means is that it's not defined that way. Whenever we talk about square roots are non-negative by definition. So like when I say, hey, what's the square root of 81? You don't say plus or minus 9. You don't say -9. You say +9, because that's the non-negative number that when squared equals 81. Okay, so it's kind of a little definition that's working behind the scenes there. Now, as far as odd roots go, we don't care. Odd roots can be negative if they want to. In fact, yesterday at the end of class, we were dealing with, let me scroll back up there. We were dealing with a good-looking example right there of an odd root that could be negative. The cube root of -125 is -5, because -5 cubed is -125. So odd roots don't have this stipulation. Odd roots can be whatever. Okay, so part B right here, easy enough. It's just n. Part D right there, easy enough. It's just y. You know, the fifth root of y to the fifth is just y. But if I'm looking at part C, what do you think? The fourth root of p to the fourth should be the absolute value of p. And the absolute value is there to maintain, non-negativity, so that the left side and the right side end up equaling each other when we do that sort of little experiment. Okay, I know that's a lot of like behind the scenes kind of background work. Suffice it to say, it's important for us. And probably over the next month, I will at least 20 times I will remind you square root of x squared equals not just x, but equals the absolute value of x. And you'll kick yourself a few times for forgetting it, I know, but it'll come home. We'll drive the point home soon enough. All right, now with that being said, let's look at another couple of examples. Okay, let's look at another couple of examples. We got x to the sixth as my radicand here. It's under the square root. So much like what Lewis just said, James, I'll throw this one your way. Can you think of something that when you multiply it by itself, James, gives you x to the sixth? How would you split that up as two identical factors? James Jacobs.
I don't know.
All right, so like x to what power times x to what power? If it were x times x, that would be x squared. So what do you think? X to the something times itself. Jack McBee, maybe help him out a little bit. What do you think? X to the...
X to the second times x to the third.
All right, well, okay, so first of all, x to the second times x to the third would be x to the fifth, because we add our exponents. Remember that, okay? And then also, I'm looking for two identical factors. Remember that last example we were talking about with Lewis, the square root of 25 equals 5, because you could split it up and say 5 times 5 is the same thing as 25, right? Two identical factors. So can we amend what Jack just said? Instead of x squared times x cubed, what do you think, Jack?
X to the third times x to the third.
That boy, yeah. So like x cubed times x cubed. And so, oops, missed the mark on that one. Because we can split that up as two identical factors, we would say, oh, okay, well, x to the third would be my answer there. And then I got to put my absolute value signs on it to ensure non-negativity, okay? And you might say, by the way, well, wait a minute, Coach, I don't get that. Why do you still need the absolute value signs? What if we said, like, let x equal -2, okay, just for kicks and giggles, okay? -2 to the sixth power is 64. The square root of 64 is 8. So the original problem would equal 8. If I don't have these absolute value bars in here, -2 cubed would be -8, which does not match up. So that's why I have to have the absolute value bars in there to ensure that non-negativity, okay? Now, that being said, could y'all kind of think similarly about part B here, right? Split up the square root. Grove, is your mic working, by the way, Grove? I'm going to take it as a no then, since I don't hear anything from Grove. John, Zweig, how about you? Is your mic working?
Yes, sir.
All right, sweet. John, how would you want to split up y to the 16th?
Y to the 8th times y to the 8th.
Yeah, that boy. Very good. Y to the 8th times y to the 8th. So the square root of y to the 16th would be y to the 8th, because that's the expression that when multiplied by itself would give me y to the 16th. Now, here's another thought question. Okay, I'm going to throw this you guys' way. So why did I make a big deal about including absolute value signs on the first answer there, x cubed, but I didn't bother with it on the second answer there of y to the 8th?
Because x cubed had an exponent that was odd.
And an odd exponent leaves room for, it leaves the door open for a possible negative answer. Jake, that's very astute. Good observation. Y to the 8th, it's non-negative just in its having an even exponent, right? We've all learned that before. If you have something raised to an even exponent, it's going to be, non-negative. Anything raised to an even power is non-negative. So the 8 right there already takes care of the fact that I need it to be non-negative. Okay, I don't have to include absolute value signs. Okay? Now, similarly, y'all look with me down here at the second two examples down here at the bottom of my screen, 8.15. And why don't we, I'll give you guys about a minute. Why don't we try those two examples? You got square root of y to the 18th, and you got square root of z to the 12th. See what you get there. It is snowing its tail off right now at my house. Is it snowing at you guys' house? Nate, can you, Nate, you got a mic that works? Alex, what about you? Mossy, does your microphone work? I'm trying to call on some of you guys that don't have a, your camera's not working, but maybe your mic works. I'm striking out all over the place. Drew, I'll throw it back your way. Drew, what'd you do on part A here? Y to the 18th, how'd you split that up?
I split it up into 9 and 9, and then split that up into 3 and 3.
Oh, that's interesting. Now, if you don't mind me asking, why'd you split it up a couple times? Because I was going to go with you on that. The square root of y to the 18th is y to the 9th inside the absolute value signs. Talk to me a little bit about what made you split it up even further.
I just saw that 9 was a perfect square and thought I should square it.
So that's a great point. I'm glad I was hoping you were going to go with that. Check this out, fellas. What if I gave y'all the square root of 81, right? Square root of 81, we all know that equals 9, right? The temptation sometimes is to overdo it, right? To think, well, 9's a perfect square. I'll just break it down even further. Let's just say it's 3. The only reason I would say it would be 3 is if it were like the fourth root of 81, something to that effect. All right, so thank you, Drew. Jack McBee, what'd you do on part B there? Z to the 12th, how do we split it up?
I broke it down to c to this 6 times c to the 6.
Good. And do I need absolute value signs? All right, Jack's shaking his head. James is nodding his head. Get with a thumbs up, you guys with that have cameras, or a thumbs down. Should I include absolute value or not include absolute value? All right, Lewis, yours is sideways, bro. You make your choice. Oh, there you go. There you go. All right, I'm gonna go thumbs down because z to the 6th has an even exponent, so it's already non-negative no matter what. Even if z were a negative number, like -2, right? -2 to the 6th power is still going to be a positive 64, positive number, okay? All right, so now let's scroll over here to the right side, and let's talk about some roots of higher indices, okay? You might notice that we've been dealing with square roots a lot. Let's talk about some higher roots, okay? Now, in this case, y to the 18th, I'm not going to split that up as y to the 9th and y to the 9th and consider it that way because it's a cube root, okay? So in this case, check this out. I'm going to split this up 3 ways. I'm going to say y to the 6th, y to the 6th, y to the 6th. And since it's the cube root, that's why I'm going to be happy leaving it as y to the 6th. What's y to the 6th cubed? It'd be y to the 18th. Okay, so we can split that up accordingly. And then let's see here. Paul, what do you think about the fourth root of z to the 8th here? What would you say splits that up 4 ways? Paul, you got to unmute yourself. There you go.
Z to the 2nd.
Awesome. Very good. Z to the 2nd. And then if I've got z to the 2nd, I don't need absolute value signs, right? Because it's already non-negative because it's raised to an even power. And z to the 2nd gets the job done there. You guys take you another minute and look at the bottom 2 here. Example 817 down there at the bottom. And we'll reconvene. I'll call on another couple guys here in a second. William Edwards, can you, you got a mic that works?
Yes, sir.
All right, what'd you do in the first one?
I got the absolute value of u to the third.
Dude, rock and roll, man. That a boy. Absolute value because it's an odd exponent, right? We don't want to leave the door open. Whenever we've got an even powered root, we don't want to leave the door open for negativity, so we put those absolute value bars on there. Solid answer. Well done. All right, and then let's throw it to Luke. Luke, how do you split up the cube root of v to the 15th? What do you think there?
I did v to the 5th times v to the 5th times v to the 5th, so I got the value of v to the 5th.
Now you almost put the absolute values on there. I'm glad you hesitated and you didn't at the end, because that's a cube root, and we don't care about cube roots being odd. Being negative. Cube roots can be negative as they like. So very good job, both of you guys. Now I'm going to zoom out. I'm going to show you all four of these, and here's what I'm going to ask: can anybody come up with a shortcut? Instead of splitting it up, kind of like what Luke and I were talking about a minute ago, kind of like we did here in orange, kind of like here. Man, I'm getting tired of all this splitting it up. Could anybody cook up a shortcut that relates the original problem and the answer that we got? James, take a stab at it.
Use whatever you're taking the root of it and divide the exponent by that.
Bingo. Now, yesterday, I thought I said this in all my classes. Apparently, I didn't say it in 7th period. Actually, I don't think I said it in y'all's period either. Did I use the expression, the phrase that pays? Did I say that yesterday at all? Okay, y'all shaking your heads. Okay, so like, you ever hear these radio contests like text the keyword to such and such and win $1,000 payday or whatever. So they're always advertising those. That's the phrase that pays. You guys have a phrase that pays here, okay? And it's called power over root. Write that phrase down. Power over root. And that's exactly what that shortcut is that James was just talking about. Okay? In each of these examples, I can get to the answer quickly just by dividing whatever the power is over whatever the root is. I'll show you what I mean. Let me zoom in here. Power over root works this way. If I've got the rth root and I've got b to the p power, b for base, p for power, r for root, okay? If I want to, I can express this as b to the p over r. This is a huge deal, okay? B to the p over r as power over root. So like as an example, you look at, William Edwards had done this one. You look at part A right here, and we think, okay, u to the 12 over 4, that's u to the 3, and then we just remember, did I start with an even root, and did I end with an odd exponent? And if that's the case, I need my absolute value, okay? And what this does is this makes it a whole heck of a lot easier for us if we're dealing with something like, the 5th root of x to the, 100, okay, to where I could just say, well, 100 divided by 5 is 20. Wham, bam, thank you, ma'am. Done with the problem, okay? It's power over root. That's the phrase that pays in this context. And not to let the cat out of the bag, we'll talk about this a little bit later on this chapter, but this also opens the door up for fractional exponents, okay? Fractional exponents look like this. The square root of x, okay? X is implied to be raised to the first power. It's implied to be under the square root or the second root. So guess what? The square root of x is the same thing as x to the 1/2 power. And so now we'll start dealing with fractional exponents, and that can be a little bit of an eye-opener for you guys if you haven't ever done that type of thing before, okay? But again, I don't want to put the cart before the horse. Let's wrap up class today with 3 final examples here, okay? I'm going to move these onto my screen now. And, I was telling my 9th graders earlier today that I've got a star around example 7 because this is really where the rubber meets the road, okay? This is where you really start putting into action some of these skills that we've been practicing up to this point. And in fact, that second Delta math assignment that I mentioned at the beginning of class, it's really going to be like a drill and kill. I've got like 15 in a row of just examples just like this, okay? Now, you will use these skills that we're about to practice, simplifying radicals. In fact, that's what this is called if you wanted to write it down. The instructions would just literally say, simplify the following radicals. Okay. And you're going to use this skill next year in geometry a bunch. You'll use it in algebra 2 quite a bit. You'll use it all the time in trigonometry. It is a basic building block skill from algebra 1. So I want you guys to get really good at it, okay? Now, here's how this is going to work. You're going to look at the radicand, and you're going to look for perfect factors of the radicand. Okay, and remember the radicand is what you're taking the root of. So in the first example, it's 98. That's our radicand. We're going to be looking for the perfect factors. Okay, like for example, 98, I could split it up. Let's zoom in here. I could split it up as 49 times 2. Okay, just using a little arithmetic. Now, why would I want to bother splitting it up as 49 times 2? Because we've got, and throughout the next, several weeks, I'm going to be teaching you guys what are called radical rules, okay? Earlier in the year, we learned exponent rules. Now we're going to have radical rules. But look, our very first radical rule looks like this. If I've got the nth root of a times b, I can split that up as the nth root of a times the nth root of b, okay? The nth root of a times the nth root of b. And I like, here, I'll type this in. I like to phrase that as the radical of a product is the product of radicals. Okay, write that phrase down. The radical of a product is a product of radicals. So if I've over here in blue up at the top left of your screen, if I've got square root of 98 written up as the square root of a product, then I can chop that radical in half and do square root of 49 times square root of 2. Are you smelling what I'm stepping in yet? Okay. Square root of 49, why do I like that? Why am I considering that as a perfect factor? Square root of 49 happens to be 7. Okay. And so we can do what? This exercise is called simplify the following radical. We take out that perfect square factor 49 and we write it as a coefficient now, 7 in front of the radical 2. 7 square root of 2 is my simplified answer. Okay. Now, I want us to try this kind of together as a group. I did the first one. We will do the second one, and then you will do the third one here. Look at 48. Okay, Tiago, how do you want to split up 48?
24 times 2.
Okay, fabulous. 24 times 2 works. Let's split that up because, hey, after all, 24 times 2 is 48. And when I chop that in half, okay. Do I know the square root of 24? Do I know the square root of 2? So although that particular factorization is true, it's not advantageous. Okay, so good try, Tiago. Lewis, can I throw it your way to pick a different pairing?
12 and 4.
12 and 4. Classic answer. Classic answer. Let's do, I'll tell you what, I'll do 4 and 12. I like to put the perfect square first. All right, 4 and 12. I'd split that up as the square root of 4, as the square root of 12. Okay. And I can take this one further. I happen to know the square root of 4 is 2, so I got 2 square root of 12. And yet, that would not be a correct answer. Similarly to how, like when you guys were in elementary school, y'all learned that like if you had 100 over 200 and you said, "Oh, teacher, I've simplified my fraction out. It's 10 over 20." You simplified it, but not all the way. Okay. So you know what? I'm a giving man. I'll give you a chance, Lewis. Can you take 12 and can you split 12 up any further?
4 and 3.
Hey, there you go, that boy. So we have our coefficient of 2. We can't throw it out, but now we say 4 and 3. So square root of 4, square root of 3. Square root of 4 is 2, so I got 2, square root of 3, and I got, I can barely get it in there. Yes, okay. So 4 square root of 3 would be a good answer. So in blue, we kind of struck out. Didn't have anywhere else to go. In green, we took our sweet time about it, but we got to a good answer. Jack McBee has his hand up. Jack, what do you think?
16 and 3.
Hot dang. Jack's got it. The most efficient route to go here, fellas, is to pick the largest perfect square factor that we can, okay? Because the square root of 16 is 4, and I get my simplified answer a lot quicker, okay? So with the square root of 48, we can be more efficient. Now, look, I got to be honest with you. Make a note to this effect that it really does matter what kind of root you're dealing with as well, okay? So like you could, if I had thrown this one at you, the cubed root of 48, 16 and 3 wouldn't work anymore, okay? Nobody told me but to try this one, but look, 8 and 6 would work in this case. Cube root of 8, cube root of 6, cube root of 8 is 2. And so depending on the root that you're dealing with, it's going to dictate what kind of pairing you choose when you're splitting it up as the radical of a product, okay? So last example for today, we've done one together. I'm going to have you guys do example 8.26. See what you guys think about square root of 45. Take you about 30 seconds, see if y'all can work that one out. Jack, your hand is still up, by the way. Andrew, do you got, first of all, Andrew, does your microphone work?
Yes.
Awesome. And then can you tell me how you split yours up?
I thought of 3 and 15.
Okay. 3 and 15. Neither of those is a perfect square, so I'm kind of stuck after that. However, okay, I could split 15 up again, right? 15 is the same thing as 3 times 5. And then I could group these two guys together and get the square root of 9, which is 3. Okay, so that is doable. And to be honest with you, we could have done the same thing over here with the 24. We could have split the 24 up further, but it would have taken a while. So Andrew's correct in a way, sort of a long, drawn-out way. Paul, what pairing did you pick? Paul, I see that you've got your hand up. It looks like you want to answer, but your mic's not.
Oh no, I have a question about 48.
Oh goodness. Okay.
What was the problem with 16 and 3? Like
what do you mean? What was the problem? That was the best way.
Oh. Okay.
No problemo. Paul, while I've got you on the phone here, can I sell you a time? No, I'm not kidding. I'm kidding. Paul, can I get you to tell me about 45? Like, how would you split up 45? 3 and 15 doesn't work as well.
I would have picked 9 and 5 as my starting.
9 and 5 sounds great. So 9 and 5 gets me more directly to the answer. We saw that come up in I think Andrew's example, right? It just took us a moment or two more to get there, a little bit longer to get there. Okay. Now, fellas, our class time's up. We've hit about 35 minutes today, which I'm gonna call it quits on this lesson. But look, what do I want you to do for homework? I want you to go to Delta Math and find you those 2 assignments from 8.1. Okay, and on for tomorrow's lesson, we will continue on with some more info about radicals. You guys got any questions before I let you go? Hey, then I'm going to cut you loose. Thank you again for a great class, fellas, and live Jesus in our hearts forever. Take care.